Hello friends, our noble quest today is to actually retain the OSI TCP IP model basics, aka how networks like the internet function. If you're having trouble getting the network layers to stick, or like me, you have an on and off love affair with Cisco packet tracer courses expiring, then this one goes out to you. Step 1. Networks are like onions.
Layers! Onions have layers. Ogres have layers. Onions have layers. You get it. We both have layers.
Just like learning sheet music, we'll start with an acronym that you'll remember. All people say they never download popcorn. Hint, that last word might not actually be popcorn. For those of you who don't get it, I'm sorry. For those of you who do get it, I'm also sorry, but you'll remember it now, won't you? So, when we're sitting at our computer first accessing a program, we're going to open an application. For example, browser, Firefox. We type in youtube.com and see that HTTPS, which is an application layer protocol. Now, coders would care about breaking up the application layer into two more pieces, which the OSI model does. What's in the browser will be presented to us using particular data formats, example HTML, JPEG, PNG, PDF, MPEG, and so on. So if I asked, which image type can have transparent backgrounds? That would be PNG. The presentation layer also cares about encryption methods. So in our case, the S in HTTPS stands for secure. The encryption method source for this comes from the SSL or TLS protocol. However, great example, the SSL and TLS protocols don't just encrypt, they also prep for communication sessions between the application data on both devices. It's the session layer that cares about authentication, that each browser tab only opens the data stream meant for it, and that different streams destined for the same application are tied together. For example, audio and video data streams are in sync when you're watching live content. Now that we're past the programmer level layers, let's get into the real TCP/IP, how data is labeled, shipped, and delivered. Step 2. A net works when it's
Mail time! The mail's here! Here's the mail that never fails. It makes me want to wag my tail. When it comes, I want to wail. Mail!
To Meg Griffin.
For this part, we're going to borrow a packet tracer file from a favorite YouTuber of mine, Network Chuck. Please go check out his channel and consider buying some Network Chuck coffee. Now, this is the part in most videos where you go down and up the layers one time and it's over. You wish. We are going to step through not just every hop from typing in a domain to seeing that main page, but also the TCP/IP layers involved in each hop, including the domain name server request. Basically, this is an opportunity to etch this into the grooves of your brain. Packet tracer simulation viewing best practices. First, we're going to open the simulation window and make sure that we're only looking at DNS, HTTP, and HTTPS traffic. We're going to open Johnny's laptop, fakey browser, and type networkchuck.coffee and hit enter. I recommend forwarding up until right before the website populates and then immediately closing the web browser. Otherwise, it will keep simulating endlessly, and you might not know where we're supposed to end. Now, to see where we are in the simulation, we can either click through the @ device column, or we can backtrack to the beginning of the simulation and click on individual messages. I would recommend the latter, otherwise the network diagram progress won't match what's happening in the @ device window. Finally, we can start at Johnny's laptop and see what's going on. First thing you notice, there are only out layers. Johnny's laptop needs to reach the domain name server to find the IP, the internet protocol or logical address for networkchuck.coffee. The second thing you notice, layers 6 and 5 are grayed out. That's because transversing the actual internet doesn't involve breaking out those presentation and session layers like the OSI model does. No coding detail here. Again, TCP/IP only cares about mail time. So Johnny's laptop will start at 7, the application layer. This is our DNS request from the browser. Let's pretend it's a letter. Dear nearest domain name server, I would like to know the IP address to get to domain networkchuck.coffee. Hop down, layer 4, transport. When we mail our letter, which postal service are we going to use? The government postal service, a private company, which one's more reliable, has better tracking, which one's faster? Well, TCP and UDP are exactly like that choice. Transmission Control Protocol has a more thorough acknowledgement process, and User Datagram Protocol is better for instances like VoIP, where resending a missed piece of data causes more harm than good. So, do we care if our request is dropped? In this case, not really. We can always send another one. For our simple domain name server request, UDP will do. Also, note the ports shown at layer 4 are not physical ports, they are logical ports. A simple search on well-known ports will come up with what port 53 is used for, DNS. Let's add this transport information to the header and footer of our request, or encapsulate it. Now, with this head and tail, this altogether is called a segment. Layer 3, network. Yes, finally, IP addresses. At this point, we've encapsulated our segment into this lovely packet. We're going to put our source IP for Johnny's laptop in the return area, which it got from the logical transport layer port. And then the destination IP is known because it's in the same subnet, or neighborhood of IPs. Layer 2, data link. We have encapsulated our packet, which had all of the IP information or layer 3 addressing, into this frame, which will add the media access control addresses or layer 2 addresses. Every network interface has a port or ports, each with its own MAC address, making it a truly physical address. Now, how do we get those source and destination MAC addresses from those given IPs? The answer is IP to MAC and vice versa needs to be resolved with a process called Address Resolution Protocol, or ARP. Either a device has this data stored in its ARP table, or it needs to send out an ARP request. In this case, we have both the source and destination MAC addresses in our ARP table. If we didn't, then an ARP request would need to be sent out while our packet waits, but thankfully, no need. So now this is our frame. Keep in mind that destination MAC is going to align with a physical port that the switch stores in its layer 2 CAM table. Get it? It's the opposite of MAC. So that would also tell you why a specific physical port is being used. Layer 1, physical. The laptop has that physical port to send the frame. We won't discuss it in this video, but there are a host of material connection details and limitations that involve capacity, speed, distance, all which affect the success of the network. So now we're at our local switch, which is only going to touch the physical layer and MAC addressing. The switch is going to receive that frame and say, not for me, who do I forward this to? And for the sake of this brand new hypothetical network, it hasn't ever sent to the DNS server before. Therefore, it's going to flood the frame onto all ports in its local network, except the sending port. Fun tip, you might be wondering why these ports have 2 digits with a slash. Well, switches and routers can have multiple rows of ports called slots. So you start at row 0, for example, and then have maybe port 3 from left to right. The next row would be 1, and so on. Sometimes there's even a 3rd digit to indicate a chassis extension, but not in our example. Okay, so we've flooded all ports except the sending port. That means we sent a message to the router, Lisa's laptop, Denny's, Mark's, and the actual DNS server. Now, devices for Lisa, Denny, and Mark will read that frame and say, this isn't for me, and toss it in the recycling. The recycling, not the trash. But the DNS server will read it and say, this is for me. Yes, that's my MAC address layer 2. Yes, that's my IP layer 3. Okay, this is UDP layer 4, so I don't need to send an acknowledgement or reassemble data in a set order. Oh look, layer 7. They want to know the logical address for networkcheck.coffee. I totally have that. Dear Johnny's laptop, here is the IP address you requested for domain networkcheck.coffee, 23-227-3865. Pleasure doing business with you. Sincerely, your local DNS server. Layer 4, transport. The server is going to put the same header and footer on, but now the source is DNS 53 and the destination logical port is UDP port. So they've switched. Layer 3, network. My IP as sender, Johnny's IP as destination. Layer 2, data link. What was Johnny's MAC again? Oh, I have that in my address book now since he just sent me a letter. That's ARP again, but no need for a request since I have it. Let's mail it on this physical port. Next, we're back at the same switch. Getting the hang of it now? Receive on the physical port. Layer 2, I recognize this destination MAC address. I'll forward it directly out this port. Back at Johnny's laptop, mail for me. That's my MAC address on this frame. That's my IP. Right, we used UDP for transport. Wow, my DNS request. I can now ask for things from the domain networkchuck.coffee. Let's prep an HTTPS request right away so we can see their webpage. Dear networkchuck.coffee, I want to see your website homepage. Now, last time we were at transport layer 4, remember that the DNS query used UDP connectionless protocol. But for the actual website data, we really do care if any segments get dropped because it won't be reassembled correctly. So we're using TCP, the connection-focused protocol. Layer 3 network. That's our source and the new IP we got from the DNS server, 23.227.38.65 on our packet. Layer 2 data link. We have our source MAC, but wait, where is that MAC destination? It's not Network Chuck Coffee. It's actually the next router on the route to the website. But why? Well, it's because layer 2 can't see outside the LAN, and ARP is a layer 2 protocol. In short, it can't register what MAC goes with that IP. It only associates that destination IP as coming from the gateway to the internet. So this is a critical moment. The first time so far we've seen the final destination IP encapsulated within a MAC that isn't also the final destination device. They don't match. Instead, it's the MAC of the nearest router because our local network can't see anything outside of itself. We need a router to get us to a different IP neighborhood or subnet. Physical, it buffers the frame and then sends it out to the local switch. The local switch physically receives the frame and forwards to the router MAC address, likewise needing that router to reach outside of the LAN. Layer 1, the router physically receives the frame. 2, it recognizes that's my MAC address, for this particular network interface at least. 3, that's the networkchuck.coffee IP. Ah, that's my IP neighbor in my adjacency table, so I already have its MAC address. Important note, routers actually have MAC addresses assigned to every single port, not just the device as a whole. So that can help explain why the source MAC address has changed from the in layer to the out layer. 2, the CAM table tells me that MAC address should be sent out on this physical port. At this other network switch, we're now in a new LAN. Technically, we have been ever since leaving that router port. Although, in a real-life scenario, there would be multiple routers, at least 2, representing each LAN's gateway to the internet. Anyway, Network Chuck subnet also contains a switch, and as the router indicated, it's just going to forward everything over the data link layer to reach the Network Chuck server. The new switch physically receives the frame. The destination MAC is in the CAM table, so it forwards the frame out the correct physical port. Finally, we've reached the website server. The server receives the frame and says, yes, that's my MAC, layer 3, that's my IP, 4, oh, this segment is using TCP and requests I acknowledge my receipt. I will pay attention to the sequence numbers so I can reassemble everything correctly before sending it to the segment port, which is for HTTPS. 7. Oh, HTTPS, Johnny wants to check out my homepage. That's my whole purpose as the Network Chuck server. I will serve him this homepage. 4. Okay, my new segment comes back from the HTTPS port and will also be TCP, so I'll follow the protocol and give it sequence numbers. 3, our packet will now have the sender and destination IPs switched. The server automatically recognizes the destination IP is outside of its LAN, so it will send the packet towards the gateway. 2, so again, that's why the destination MAC is for the right side of that router and doesn't match the final destination IP for Johnny's laptop. 1, the CAM table recognizes the way to the router is via that particular physical port. 1, we receive. 2, read the frame. That's not my MAC, but my CAM table says this physical port is for that destination. Back to 1, send out that port. 1, the router physically receives. 2, checks the frame 2 area. That's my MAC address for that port. 3, opens it up. That's not my IP, but I have it in my routing table. Back to 2, let's relabel the destination MAC for this side of the LAN. Thankfully, Johnny's laptop is adjacent, just switches between, so we're almost done. The CAM table tells me to send it through this physical port. Send. The LAN switch in Johnny's network receives the frame and says, that destination MAC is in my table. CAM says it goes down this port. Send. Finally, Johnny's website request has been delivered. The laptop physically receives it, reads the frame, that's my MAC, opens it, reads the packet, that's my IP, opens that, reads the segment. This is coming from HTTPS and destined for TCP. Opens. Our website landing page is finally loading. Ay caramba, that was an amazing journey. Thank you for hanging in there and for always giving it your best. For now, all you can do is repeat the video. Go look up terms you're unfamiliar with or things you have questions on. And until next time, TTFN or ta-ta for now.